Alright, thanks for joining me on our day off. So, remember the last topic we talked about on Wednesday was amine oxidation and how we can go from no bonds to oxygen to 1 to 2 to even 3 bonds to oxygen to get our nitro group. We can do this with lots of different reducing agents, including H2O2 or KMNO4 or what else did we say? Oh yeah, MCPBA was another one that we could use for this type of oxidation. What's cool is if you take a tertiary amine though and oxidize it, you get an amine oxide, which is a nice bulky amine with its own base. So if you do this on a tertiary amine on a substrate, okay, again you oxidize it, it has this bulky leaving group with its own base, and it does this really cool intramolecular E2. That's called the cope elimination. So that was the last topic we got to. Now I wanted to move on to arenediazonium salts. And these really could have been back when we learned about EAS and all those useful reactions. But this specifically deals with amines, and so it's here. And so, as it says here, aromatic amines are very useful in synthesis due to their ability to become arenediazonium salts. And what I mean by aromatic amines here are anilines, which look like this. This is aniline, right? And what's really cool, well, first off, to make the arenediazonium salt, here you go. You have your aromatic amine. Throw in some sodium nitrate, NaNO2. You also need some acid, 2 equivalents of HCl to be specific. And what we get out is what's called an arenediazonium salt. Okay, so we have a plus here. The salt part, we have a Cl minus to counteract, to be the counter ion for our plus charge there. We also get 2 H2O plus NaCl. And this right here, this N2 group on the arene, or on the aromatic group, that should have been Ar. This is the arenediazonium salt. Arenediazonium salt. Alright, how does this reaction work? It's kind of steppy, especially with some protonation, deprotonation steps, but it's not too bad. So you start off with the sodium nitrate first, NaNO2, okay, and that minus charge in with the HCl. The first thing that's going to happen is we're going to go protonate, okay, and actually this happens again. So we need 2 equivalents of HCl. We're going to make this a super good leaving group on here, that protonated water. And so once we have made protonated water on here, like I said, we make it a super good leaving group. What's probably going to happen? It leaves, which means we get H2O, as I said up here. We get H2O, and we get what's called a nitrosium ion. So it looks like this. NO, the plus charge in the N, because we took electrons away from the N, but it's in resonance with this guy. And triple bond O, with the plus charge on the oxygen. Okay, this is the nitrosium ion. Nitrosium ion. Okay, this guy is in a really good electrophile. Good electrophile at the nitrogen. So let's go and use him, just like we did in EAS. Okay, here's our awesome electrophile. Now we do EAS. So then we have our, not quite EAS, but close to it. But we have our amine. Okay, obviously the amine lone pair is much better, is a much better nucleophile, much more nucleophilic than the benzene ring. So when we have our amine versus the benzene, it's going to be the amine that's the better nucleophile. And so it attacks our awesome electrophile. Okay. A-R-N H, H, N, double bond O. Okay, then we have a plus charge here. We have water in there from earlier, which will go and deprotonate this guy. Okay, we're almost there. It's actually a few more steps. Not quite as, intuitive as we might have thought. But now all we have to do, if you look at the product versus where we're at, we have to lose this oxygen. So, just kind of like we did before, we're going to make it a good leaving group. Okay? So we just made some H3O plus in protonating water. So we're going to go protonate our oxygen now. Whew. Here we go. ARNHNOH plus now. And this guy is in resonance. So this is kind of looking like a Wolff-Kishner when we are in resonance with this guy. ARNHNOH. He's now got a plus charge here on the nitrogen. And so we go and deprotonate him. I know, it's a long mechanism. I agree. I don't think I actually realized how long it was. N, O, H. And we do it one more flippin' time. Again, all we gotta do now is lose this OH to get to our product. So, again, we go and protonate. H, OH2 plus. I'm trying to be faster now. ARNNOH. It's a good leaving group now. And so if we just take these electrons on nitrogen and kick them over to kick off. Whew, finally. ARN2 plus H2O. Whoa. Sorry. Yes, that was a long mechanism. Also not very intuitive. Darn it. Okay, but the cool part isn't really getting here. The cool part is what we can do with this guy. Okay, again, these arenediazonium salts are very, very useful. Okay? Because from these arenediazonium salts, we can use all these different reagents to get all these functionalized aromatics. Look at this. We just take our diazonium salt in with some acid, give it some heat, and we get an alcohol out. We throw in copper chloride, we get a chloride out. Throw in copper cyanide, we get a cyanide out, aromatic cyanide, okay? Throw in some H3PO4, look at this, we get rid of the group altogether. That's interesting, I think, that you would go from an aniline all the way to nothing, okay? Using just these different reagents, okay? And what's both cool but also not so cool is that we can do so much with this, okay? So the bottom line is, yes, you do need to know all of these reagents. Yes, you need to know all. You need to know all. So break out those flashcards, start practicing, because unfortunately, I am not going to provide mechanisms. Because to be honest, they're steppy and they're not very well known. Can't provide mechanisms. Okay? So again, you do need to understand how we make the arenediazonium salts, how we get to here, okay? And that's just a bunch of protonations and making oxygens a good leaving group like multiple times. But then once we get there, get out your flashcards and start learning these reagents to make all these functionalized aromatics, all these functionalized benzenes. And that's where these are super useful, is making all of these functionalized aromatics. Okay, so let's show this amazing stuff in all of its glory. Remember how we put amines on to aromatics to begin with? We first would need to nitrate the benzene. You do that with nitric acid. Remember, You need to use 2 super strong acids. Nobody wants to do this reaction. But that's how we put on the nitro group. How do we go from the nitro group to the aniline? You guys remember? We do that via reduction with zinc HCl, and we learned in this handout that we can actually use lots of other reducing agents to do this, like LAH and other such ones. Now from here, this is where we do the arenediazonium salt formation using sodium nitrate and HCl. Right? This is how we get to the N2 on here. And then from here, we can use various reagents to put on even more different things onto the benzene. More groups than we already even know. Okay? Various reagents put us here. Z with various products. And just as it says there, holy crap, we can now make a ton of aromatic compounds. There's really no other good way to make some of these compounds. There's really no other, we don't know any EAS reactions that put an alcohol on there. We do know EAS reactions to put chlorines and bromines on there, and fluorines and iodides, but cyano groups to get an H out, and these are really cool. These are coupling the aromatic groups. We don't know any other good ways to do this. So that's why these are super, super useful. So here's an example. I have multiple. This one's actually a named reaction. When you take the amine, I'm not going to go through all the steps to make the amine. You take an amine, or the aniline, and you throw in NaNO2 to make the arenediazonium salts, HCl, and then you throw in the copper chloride. If you look back onto that table as to what this installs onto the ring, it is a chloride. This is actually called the Sandmeyer reaction. Sandmeyer reaction. This is one I always had a hard time remembering in graduate school, and people would refer to it, and I'm like, oh yeah, I totally remember that one. But I totally didn't. Okay. How about this one, when we have an amine on there, as well as a deactivating group? Okay. Again, we make the arenediazonium salts, NaNO2, HCl. And then just add in some acid and heat, H2SO4, H2O, and heat. And what do we get out? Look back on the previous page. The deactivating group stays there. But now our amine turns into an alcohol. And I wanted to say here that when you do this, you have to be very careful to do this second reaction here, because the diazonium salts, these are actually really explosive. I've said that before, how these azides are really explosive. So, you know, again, good times in the lab. How about a multifunctionalized benzene? Ethyl, CO2H, with our amine. And again, make the arenediazonium salt. Okay. Put in H3PO4. This is that cool one I told you about that gets rid of the amine altogether. ET-CO2H. Look out for these in synthesis. How do you get rid of a group? How do you get rid of it? Make sure it's an amine. Just make it into the arenediazonium salt. And then throw in some phosphoric acid. Oh, and here's one of those coupling reactions I just mentioned. So let's say we have our arenediazonium salt already made, plus charge with our Cl minus. So I've already made it from the amine. And let's say I have this compound. This is SO3 minus. It's a stable functional group. And then I have this other aromatic group, NME2. These two are just going to couple through the diazonium, and this one is an ortho-para director, and so it makes this molecule. And Me2 at the para position because the orthos are a little bit more hindered. SO3 minus, and I did this one as an example because this is something cool. This is methyl orange. It's a dye. I actually just, that softball tournament, or that softball league I told you guys about that I'm not really all that proud of, we got orange champion shirts. They're actually kind of ugly, but regardless, this is the dye that that's probably used on the fabric to make it look orange. I also have written down that it can be an indicator in solution. Cool. Really quick, last example. How about a synthesis problem? Since we're not limited to lecture time, I can add this one. How about this guy going all the way back to benzene? Okay, so we're going to use a mixture of our EAS reactions as well as our cool newfound diazonium salt reactions, okay? So the only way we know how to put on an alcohol onto the benzene is using our cool newfound diazonium salt stuff. So we have to go back to the amine as the first step backwards. NH2Cl. Okay, so we do this by first making the diazonium salt, NaNO2, HCl, and then look back at the table. What do we need here to do this? To make the diazonium salt into the alcohol, it was just water and heat. Okay. Now from here to go back, right, this guy is an ortho-para director, but how do we get the chlorine meta? How do we make amines? We can't make amines directly from benzene, right? We make amines through the nitro group. And isn't that useful because the nitro groups are meta directors? So we do this again with just reducing HCl. Again, we can do that with several other different reducing agents. Now we can go back to the nitro and install the chlorine, working backwards. NO2. This is really easy, right? Cl2, AlCl3. And then we go back to benzene. And this is, oops, keep doing that. HNO3, H2SO4, the one with all the acids that nobody wants to do. That's an H. Cool. Thanks for hanging out. Hope you guys have a good weekend. Go do the cool activity because you get extra credit. Okay, bye.